And first of all, I would like to thank the organizers for inviting me to this conference, and it has always been a pleasure to visit Korea. Today I want to try to discuss the issue of the linkage between soil processes and planetary health. So first of all, planetary health is really a new term or new subject. About 3 years ago, Lancet commissioned a report on how to safeguard human health in this new era. And in this report, they developed the concept of planetary health. It's really very well aligned with another concept is One Health. So if we want to make sure that human health, we should also ensure that the ecosystem is healthy. Even you are a healthy person, you live in a contaminated environment, eventually you will become unhealthy. So the concept of planetary health is really to address the linkage between human civilization and the natural environment. So the health of human being is deeply rooted in the natural environment. So we are in the same system, in the planetary system. And because of the human activities, actually, on the one hand, we rely on the natural ecosystem, but on the other hand, we are degrading the ecosystem, and the ecosystem is taking actions to reverse and have impact on our health system. So I think that we need transformative actions that we can protect the present and the future generations by safeguarding the ecosystem health. So in particular, I think solutions, we heard about solution-oriented research. And in this particular subject, solutions lie within reach and should be based on the redefinition of prosperity. Prosperity is not about just the convenience. I always say that the convenience is apparently an enemy of many of these, or the cause of many of these environmental problems. For convenience, we have plastic bag everywhere. For convenience, we have disposable cups we are using every day. So I think we needed to redefine prosperity and focus on the enhancement of quality of life and the delivery of improved health for all, together with respect for the integrity of natural systems. So this is also in the Chinese government now, we are promoting the idea of eco-civilization, which pretty much saying that the entire planetary system is one common future that we have to preserve. So planetary health, the concept is really try to connect the dots. So here I use a picture from Lancet, from the website of Lancet. There's a few examples illustrate the linkage, which is not apparently for the general public. And for we scientists, we try to convey the message to the public. For example, air carbon dioxide can actually affect our nutrition. When we have elevated the carbon dioxide, plants grew quicker and more biomass. However, the trace elements which are critical in our health is not being taken up proportionally to the improved biomass. So that under increased carbon dioxide concentration in the air, there is a danger or there is a risk of malnutrition due to trace elements. And for example, land use type, there's a dementia risk linked to living close to the road. You have noise, you have air pollution. So these are very important. And also, here's cardiac admissions actually increased in period of worsening drought. And there's ecosystem processes contributing to this linkage. And of course, we all know that active commuting and inhaling air pollution. The active commuting is good in terms of exercise, but if the air is polluted, then there is a confounding factor of the eventual outcome of the health. And for example, here they talk about the bee population and human deficiency in vitamin A. Not quite apparent, but ecologically they are linked together. So this diagram actually shows that under this concept of planetary health, the health of the person is connected with so many factors in the entire planetary system. So this diagram essentially illustrates the connectivity of human health and the ecosystem health. And I'm a soil scientist, so my focus is on soil. And we know that soil can affect human health in different layers of ecosystem services. First, we know that soil is the basis for plant growth. So it's the origin of food supply. But not only that, the soil quality actually affects the food quality. For example, trace elements like selenium. In Finland, the soil is deficient in selenium, so that the food is deficient in selenium. People have problem in selenium deficiency. So only if you apply selenium fertilization, you can improve the ecosystem services of soil. And as with human activities causing soil pollution, that will also influence the quality, the safety of the food. But not only that, the soil pollution will affect the environmental security. So pollutants can be transported to the air or to the groundwater and the surface water. So this is the entire soil ecosystem services linked to human health and well-being. Just an example to illustrate the whole, the basic soil ecosystem services for food supply. We know that the Fertile Crescent is regarded as the cradle of human civilization. And that exactly illustrates that the food supply from the soil, fertile soil, is so important. Only when we have enough soil, or enough food, people can diversify their specialty. People can work on other industries or other art or literature, because other people can produce enough food from fertile land for the subsistence of the population. So this is the first layer of the ecosystem services we are talking about. But we also have, as I mentioned, that the soil plant system, they take up nutrients and also other contaminants into the plant and also affect the human health. And here I just want to illustrate one of the topics I have been working on in the last 20 years about arsenic. So modern civilization has extracted the arsenic from groundwater or from mining, and the arsenic is an impurity. They are introduced into the surface, Earth's surface, into the agriculture system and into the water system and also in the air. So eventually we have global contamination of arsenic due to this civilization, during the civilization. Just one example, we have soils we collected from central China impacted by mining activities. You can clearly see that the concentrations of arsenic in the rice grain that the kids are eating in this region is elevated more than 200 ppb, which is considered as unsafe as a subsistence food for the local population. And we also look at this exposure of arsenic through food ingestion. We think that consume 200 grams of rice containing this level of arsenic is almost equal 2 liters of water contaminated with 10 microgram arsenic per liter. This is the global standard for water arsenic. And this is only the medium level of arsenic in rice. You can see that If arsenic level is over 100 ppb, there's almost 25% of the samples from the Chinese market actually is over 100 ppb. So it's exceeding equivalently to consuming water containing more than 10 ppb arsenic. So you can see that the soil pollution actually is contributing to the health outcome of the general population. But this is just a quick example to tell you the linkage between soil and human health. And today I want to focus more on the soil biota, which is more like a cross-cutting issues related to the soil ecosystem services. Soil biota can contribute to environmental remediation, can contribute to soil fertility, but soil biota can also have direct impact on human health. The microbes from the soil, if they grow on our skin, can increase our immune system, improve the health. So when people move from the rural environment to the urban, they have reduced the contact with nature. There is a higher rate of allergy. And there's already data to show that the reducing the nature-human contact and likely due to the less exposure to the natural microbial community is causing some of the health problems in big cities. There are a number of ecosystem services related to soil biota I've already alluded to. First is nutrient transformation and availability to give the soil ability to grow enough food, but also they can play an important role in decomposition of organic matter, soil fertility, and the stability of the soil, and the biotransformation and the degradation of pollutants for bioremediation at a global scale also. And importantly, we can also discover drugs from the soil. And in fact, the very first, one of the first antibiotics actually were discovered from the soil. So bioactive compounds and other health benefits, as I have mentioned, the immune system can be delivered by the soil biota. So here I want to show the relationship between antimicrobials and antimicrobial resistance. So this soil biologist in the 40s, he discovered the streptomycin from the soil, and this actually led to a Nobel Prize. In fact, it's the only soil scientist who won the Nobel Prize in the history. And more recently, there are many studies now coming up because there is a global risk of antimicrobial resistance. We needed to find more antibiotics from the nature. So this is a study from the United States. They take samples across the United States, New York, and in the parkland. They can even find that in the parkland soil microbiome, there's a genetic information or the genetic machinery that can be utilized to produce bioactive compounds, such as antibiotics, immunosuppressants, and also anti-cancer, etc., etc. These compounds can be discovered from the soil. And another study published this year in Nature again demonstrates that using these metagenomic tools, they can map out some of the microbial taxa which have not been discovered before, that they can synthesize this bioactive compound. So that demonstrates that in the soil there is a great potential of discovering, we have the opportunity to discover new drugs from the soil environment. But in the same time, because we have used antibiotics so much in the past, there is an issue of antibiotic-resistant genes as a contaminant. So this kind of contamination is degrading the soil ecosystem as a reservoir of bioactive compounds or other microbes, so that the diversity of the ecosystem is being damaged due to environmental contamination. So for this instance, I will elaborate a little bit furthermore, because this is really an unconventional contaminant, because this contaminant is actually DNA information. So they can be amplified in the environment. Not like any other chemicals, they cannot be amplified. They can be degraded maybe, they can be sequestrated in the specific component. However, these resistant genes, they can be amplified in the environment because they are carried by the live bacteria. When the bacteria move to a new destination and there are nutrients, so they can proliferate and the genes will be amplified, and there's opportunity of spread of this gene through horizontal gene transfer. So we have been working on this issue in the Chinese environment in particular, but also through collaboration. We really work globally, looking at the sources from humans and animals into the wasteful discharge and the manure application. Eventually, these resistant genes end up in the environment, and through many different pathways, these genes can find their way into humans through potentially human pathogens. And in the end, there will be the risk of superbugs. They acquire these resistant genes in the planetary Earth system. So we very much take an ecosystem view of the antimicrobial resistance. Again, we talk about the interconnectivity and the cross-cutting issue of this contaminant. So this contaminant is not only in the soil, but also in the general environment, in the groundwater, in the river, and in nearby the hospital, in agriculture field. But they will find their way through the food chain into the humans. So this is just a study a few years ago we published that. We have demonstrated that in China, but the issue, the study was conducted in China, but the issue is really of global implication. So in the pig industry, we add antibiotics and heavy metals into the feed to increase the production and the health of the pigs. And you can see this heat map showing very much elevated resistant genes in the pig manure, and also the soil receive this pig manure as fertilizer. So clearly see that this is a major source. Another source is wastewater treatment plant. So people take antibiotics, and only 20 to 25 or up to 75% of the drug we take up. The rest will be excreted and end up in the wastewater treatment plant. They can be in the sewage sludge or in the treated water and discharged into the general environment. So this is a diagram we have just recently mapped in the entire Chinese urban population. So we calculated that based on 17 major cities, the samples from 17 major cities, and 32 wastewater treatment plants, the median value we charge everybody on average, I think per day we discharge almost 10 to the 14th copies of resistant genes into the wastewater treatment plant. And after the treatment, we can still see this level of contamination in the bacterial cell. So this is a level of antibiotic resistance in the discharged water. And this discharged water will come into the soil. For example, we look at the urban parks that are irrigated with reclaimed water to see whether there is a build-up of these resistant genes. And the urban parkland is, everybody would like to enjoy and have leisure time there. But unfortunately, after a few years of irrigation with reclaimed water, we find that there is an enrichment of antibiotic-resistant genes, sometimes even up to 1,000 times of enrichment as compared to the pristine soil in that city. So this, for example, this Urumqi in Xinjiang province, because in that park initially was irrigated with raw wastewater without treatment. So you can see the potential risk of using reclaimed water for irrigation. I'm not saying that there is an immediate risk to the general public, but certainly there is a concern if we continue to irrigate and if we couldn't figure out the way to remove these resistance genes from the wastewater system, they eventually will build up to maybe a tipping point will cause the disease and the spread of superbugs in the environment. And we know that we use organic manure, which is promoted as organic food. We use organic manure as a fertilizer, but those organic fertilizers derived from many intensive animal farming systems, as I said. We use antibiotics and heavy metals. So the heavy metals and antibiotics, they are residual chemicals in the manure. So we looked at many samples from China as commercial organic fertilizer. We want to see whether this commercial organic fertilizer are actually the source of antibiotic resistance. So you can see that this is the soil without organic matter amendment. These are the soils amended with different organic manure. You can see in terms of the number of genes we detected, it's very much increased. So there are many more resistant genes after the soil is amended with commercial organic fertilizer. And again, the commercial fertilizer is from intensive livestock system. And the problem goes back way back to the feed we use for the animal. So this is an entire system that we really should look at. So we not just look at the fertilizer itself, but the feed we use and the feed additives we use for animal production. And we know that the microbes can move from the soil to the plant on the plant leaf. So when we consume salad, we have salad at lunch. So the salad at lunch probably have microbes from the soil, and some of the microbes may contain resistance genes because these soils could be fertilized with organic manure. And also in the urban environment, the movement of microbes to the plant leaf, this is a major pathway of human microbiome intact with the environmental microbiome. So that the microbes on the green space, they might come into the human and cause maybe infectious disease, etc. But of course, we need a more epidemiological study to establish the close linkage between the environmental microbiome and human health. So I think I have probably used these samples from my examples from my own laboratory can show you that the soil quality or the soil ecosystem services can impact the human health through a number of ways, or tier the structure of the ecosystem, the delivery of the ecosystem service through a tiered structure. However, I want to even put this into a larger context of the planetary system. We have heard from Jorn this morning about groundwater inundation, which can induce the mobility of arsenic. So exactly in our soil ecosystem, if we consider within this entire planetary system, we should also consider the climate change. I have illustrated about carbon dioxide, but flooding, sea level rise will change the mobility or the biogeochemistry of the contaminants. So for example, if it is at the harvest time of the rice growth period and there is a flood, then there will be mobilization of trace elements. And when you harvest the rice under the flood condition, they probably have more arsenic than non-flooded condition. So those are the issues, not apparent, but they are interrelated. And we should really consider the health issue under this planetary system. And we also should look at the economic system. For example, when we import food from another country, the chemical residues in that country probably will move to this country through food import. And also the microbes, they can be transported. And I have a few diagrams showing that. So you have chicken farm, feed with the chicken with antibiotics and heavy metals, and there is a potential for global movement of these microbes through, for example, trading, wastewater discharge, and also international travel like us. When I travel from China, I also bring the microbiome from China to Seoul. And also wildlife migration, the birds from Siberia to other places, they can bring this microbe. And those are the issues not apparent for the general public, but they are interconnected, and we have to understand the dynamics. And also we needed to develop models to predict the dynamics of this movement and eventually the health outcome of their movement. So with that, I want to conclude my talk by emphasize that the soil ecosystem services, they are central to human civilization, but human activities are degrading ecosystem services of the global soils in an unprecedented way, such as waste discharge, wastewater or manure application, etc. And I would like to use antimicrobial resistome as an example to illustrate the problem and the interconnectivity of the planetary system that is affecting our health. And we can develop this framework for preserving soil ecosystems from a planetary health perspective. And I think that the soil ecosystem services should be considered in this entire Earth system so that we can really safeguard the integrity of the natural world. And with that, I want to acknowledge the financial support from Natural Science Foundation of China, Ministry of Science and Technology, and also the Chinese Academy of Sciences for continuous support to my research. And also, we have lots of international collaboration. For example, with the University of Leeds, worked at Leeds, they offer me the fellowship, so I travel to Leeds all the time. And also, I have numerous colleagues and students in my lab, and also international friends like Yang-Sik. We have been collaborating. And with that, I want to thank you for your attention.
Presentation. Will you take some question from yours? Okay. It is very interesting how the viruses and resistance organisms through the soil through the health. It is very interesting for me. Treatment with the organic compost. They carry the level of resistant microorganisms to human. How about increasing tendency of the organic farming all over the world?
Yeah, I think that's a big issue. I'm concerned with the general movement of organic farming. If the organic fertilizers we are using is truly free of these chemicals, then it is probably okay. But in the general practice, I think there is a great potential of this contamination from large intensive animal farming. And this is so common in the United States, in China, Europe. And so that now globally, we are trying to reduce the use of antibiotics as growth promoter. So I think there is a consensus that just saying organic farming is not good enough. We should consider other aspects of organic farming. Thank you.
Thank you. Yeah, we Please give a big hand to, okay, one more question.
Is it okay?
Okay.
As always, a great and dynamic presentation. Well done. My question is in relation to carbon in soil. What is your view about the contribution of carbon in soil to ecosystem survey? Because there are a lot of interest in storing more carbon in the soil. So what is your view on that?
Yeah. Thank you very much. In my opinion, carbon in the soil, carbon sequestration mitigate the climate change. And more importantly, carbon actually improves the health of the soil so that the microbes, they can help the cycling of the nutrients and also the degradation of agrochemicals. So I think the role of carbon has several levels. So climate change mitigation and the soil health for nutrients, but also for degradation of contaminants. So preserving soil carbon is extremely important. Thank you.
Can I have one just although I am not a soil scientist, but sir, from your presentation that you have mentioned that as the rise of the carbon dioxide, the nutrient level from the soil to the plants will be less. The concentration of the carbon dioxide for the production of glucose by the plants is also dependent on the precipitation.
Yeah.
So if the precipitation is sufficient and the carbon dioxide level is high, only then the glucose production will be high. So sir, my question is, how could we relate the production of this glucose and the level of nutrient level low?
Yeah, I think that's exactly another good point to illustrate the connectivity. So the linkage between the climate system and the food production and the food safety. So what I'm saying, the carbon dioxide enrichment causing the better growth is under the condition of appropriate water availability for the crop. So if you consider the water, then the system is even more complicated. So we are talking about the complex system, nonlinear system, and the understanding of it, I think, require new science, and that is why I think this system science is important for safeguarding human health. Thank you.
Yeah. Thank you very much, Professor Chu. Please give here.